Okay, this is the 7th and the last video on SPSS. This time we will see what is regression. Regression is a forecasting tool, well, typically used for scale variable, but not always. Let's see a very basic regression. Here we have a scatter plot between year of birth and first year of elementary school. Clearly these two variables are strongly related because typically people go to school 6 years after, even though there may be exceptions. So, first of all, you usually plot the data on a scatter plot. Then you decide, you look at the scatter plot and you decide that there may be a line which approximately passes close to all the points. Since it's a statistical tool, the line will not match exactly all the points, which is impossible since they are not on a straight line, but will pass close enough to most of them. For some of them, like this one or this one, clearly the line will be far away. So the line will be a compromise between the one above and the one below, however should pass close enough to all the points. This is the equation of the line, it's a linear equation of the line. C0 and C1 are two coefficients. C1 is called the slope and gives you an idea of the slope of the line. If it is positive, the line goes up. If it is negative, the line goes down. Okay. The problem is, what is the best line? Is this one the best one, or is it better to make it a little below or a little with less slope or more steepy or steeper? So, which is the best line? The one which passes close to all the points. There are many techniques to find the best lines. They give different results, clearly. The typical one is the minimum square technique. Inside SPSS there are clearly these techniques to determine the line coefficient. Using the least squares or the minimum squares technique, in this case I found an estimate for C0 and C1, 67.2 and 0.97. Okay, and usually regression is associated also with a famous statistical measure, R squared, okay, which gives you an idea of how close the line passes to the point. So this is the best line which is possible to find, and this is an estimate of how close the best line passes the points. It goes from 0 to 1. 0 means the points are very far away and are not on a line. 1 means the points are very close to the line. It's called R squared because it's nothing else than Pearson correlation squared. Okay, it's always positive, obviously. Okay, let's see how you can do this thing in SPSS. First of all, we open a file. This time we open example data all B. It's like example data all, with the exception that it includes some indexes or some variables which have been built in the previous video. Okay, let's wait for SPSS. Okay, the usual file. Let's see first of all the linear regression. Analyze regression linear. Okay, so you can see there are many regressions. This is the first one, the typical one, linear regression. It's called linear because you use a line. You specify the dependent variable. The dependent variable is the variable which is on the y-axis, so on the vertical axis. Usually you decide from a theoretical point of view, so there is no statistics here, there's only theory, which variables is dependent and which variables are independent. So which is the influenced variable and which variable influenced the other one. For the example we have seen before, first year of elementary school is the dependent and year of birth is the independent. Okay, leave everything as it is. Okay, there are many options, obviously, and many statistics, but usually leave everything as it is, press OK, and you get the result. Pay attention that in the result you do not get a scatter plot. We'll see later how to obtain it. So R squared 0.962, so even better than the results presented here. The The results presented here reflect the data of 2 years ago, I think. So a very good R-square. Okay. The other meaningful things are here for those of you who know statistics, TF, statistics and significance. Okay. And the coefficient 47 for the constant and 0.97 for year of birth. Okay. Which means that there is an almost perfect correspondence between year of birth and the first year of elementary school. Okay. Let's see another one which will not be so good. For example, between passed exams and year of birth. So passed exams must be here. Clearly you cannot invert them, it doesn't make sense. Year of birth cannot be influenced by passed exams. Well, passed exams could be influenced by year of birth. Okay. You see that R square now is really ridiculous, 0.014. Okay. However, the coefficient is 0.1445, so rather small. This coefficient has the statistical meaning that for each year you are born later, so each time you increase the year by 1, you increase the passed exams by 0.145. It doesn't make sense, it's too small, and the square is ridiculous also. Okay, so this is the regression. It's pretty easy and pretty straightforward. Let's see, first of all, how to draw the scatter plot with a regression line. So if you want to draw the scatter plot with a regression line, you must use the graph. There's no other alternative. Graph chart builder. Scatter. You put year of birth here. Here, first year of elementary school. Okay, you press OK. This is the usual scatter plot. You open it to edit. And the regression line, pay attention, it's not this one. Or better, it's this one. So not this one, fit line. Okay. Don't click 200 times, because otherwise you will get many lines one above the other. Okay. So the linear regression line. In this case you can see it's quite nice. Let's restrict the scale here. 1955. Also here 1960. Okay, you can see it passes very close to all the data. Let's see the other one, the one which uses passed exams here as dependent variable. Graph chart builder. So remove first year of elementary school and put passed exams. You can see data here don't seem to be so linearly related. Let's restrict, however, the scale just to have a better look at them. 55, apply, close, add a fit line. You can see the line is almost horizontal. There is a slight slope. Okay. It doesn't also make sense because older people should have passed more exams. But okay, this is the scatter plot. Okay. Another thing which usually you would like to do is plotting the standardized residuals. Okay. What are the standardized residuals? Well, if you look here, a residual is the distance between this point and the line. In this case the residual is positive, in this case it's negative. So for each point you have a residual. The residual represents the error you are committing if you assume the line to reflect the true situation. Okay. For example, here the residual of this point, pay attention, it's not this distance, but it's the vertical distance. So the residual is the vertical distance between the point and the line. Okay. Sometimes you would like to plot the residuals or to plot the standardized residuals. I don't want to enter into the topic of why would you like to plot the standardized residuals and what are the standardized residuals. It's a statistical issue. Sometimes it's required by the statistics you are using. Okay. However, if you need to do it, it's very simple. Analyze regression linear. Let's put again passed exams and year of birth. Plots. just click here, and you get the histogram of the standardized residuals. Continue. Okay. You should get an histogram. Okay, here. So for the exam, don't worry, this is what you get, and this is okay if I ask to plot the standardized residuals. If you are ever interested in why is it sometimes required, etc., etc., well, there are statistical books which explain why the standardized residual should be normally distributed, like in this case. Okay. Another thing which you may want to do is saving the residuals. It may seem incredible to you, but for some models, it's more interesting the error than the prediction itself. I have seen some of your theses where the student or the referee or the supervisor was more interested in how much the errors were rather than the model, okay, the value of the model. So you need to save the residuals somehow, and let's see how to do it. Analyze, regression, linear. Okay. Well, it's not necessary to plot them anymore. Save, unstandardized residuals. These are the real numbers. So unstandardized residuals are really the numbers. Continue. Okay. And you will have in your data a new variable which contains the unstandardized residual. For example, you can see that for this person, the distance is very large and below. For this person, the distance is very large and above. This person is rather close to the line. This person is rather close to the line also. Okay. If you plot the standardized, if you save the unstandardized residuals for the other one, this one, okay, you will see that for some people it's ridiculously high. Okay, in fact, this person probably has lied. He says that it was born in 1984 and went to school in 1999. Okay. For most of the people, it's very small. These people are the ones which went to school 6 years after. That's it. This one is a negative number. Probably it's a person who went to school 1 year earlier, 1985, 1990, so at 5. Okay. Okay, sometimes instead a linear model can be built also using several variables. So you may want, for example, regression linear, to predict past exams using year of birth, using how many practice a sport, how many days a week do you come here during exam months. So put several variables. You are free also to put ordinal and nominal variables here. However, pay attention that if you put ordinal variables, you are assuming that the numbers reflect a scale. So if you put this variable here, which goes from 1 to 5, you are assuming that 1, 2, 3, 4, 5 have numerical meaning. If you put a number like this one, sex, well, you are simply assuming that 1 is female and 0 is male. So you are inserting what is called a dummy variable. So a variable which is 0 for a group of people and 1 for another group of people. So you may insert also variables which are not scale. Ordinal variable are treated like scale variable. Binary nominal variable are okay. What is absolutely not okay to be inserted here are non-binary nominal variables, like this one. So it can be done, but it's absolutely nonsense, because if you insert this variable here, you're assuming that switching from economics and management to economics and management old is the same as switching from economics and management old to master. So you're assuming that the distances between all the categories are the same, and this doesn't make sense clearly. Okay, so you can see I've inserted several variables, and it gives me one constant coefficient and one coefficient for each variable. You can see that how many practical sport strongly influence the number of passed exams, 0.96. So the more you practice, for each sport you practice, you will pass one exam more. It's not. Let's see, R square, however, it's a little ridiculous. If you insert more than one independent variable, clearly you may not do a scatter plot anymore. Don't try to do it, it's impossible. It requires a multi-dimensional graph. So you may not do scatter plots anymore. Sometimes, however, you don't want a linear regression model, you want a regression model which has another shape, a quadratic, a logarithmic, exponential regression model. So you don't need a line, but for theoretical reason, usually for theoretical reason, or because your scatter plot doesn't look like a line, you need something else. So let's try to do it. For example, analyze regression, curve estimation, it's here. You decide the dependent, please put only one, even though many are available. Passed exams. The independent, in this case, SPSS accepts only one independent. So passed exams by how many practice sports? No, let's put another one. Participation. And here you may decide which curve do you want. Linear, so you will repeat the linear, but also logarithmic, quadratic, and exponential. Okay. Obviously at exam, please do only the ones I ask, don't do the other one. Okay. In this case, SPSS will display also the graph automatically. So this is the graph. These are the lines. Let's restrict the number of passed exams to 40 so we can see something. Okay. You can see one is linear, another one is logarithmic, you don't distinguish it, another one is exponential, you don't distinguish it, but you should distinguish, this is the logarithmic. You can see it starts from negative numbers, goes up straight. You should distinguish the quadratic also, which is the one which goes down here. Okay, they are all very similar in this case. Since in this case there is no relation, as you can see, the data have the shape of a cloud, so there is no relation. And here you get the R square for all the models. You can see ridiculous R squares. If you need the coefficient, constant b1 and b2, in case b2 exists, for the quadratic b2 also exists. Okay, so this is how to get a non-linear regression model. Unfortunately, you can get it only for one independent variable only. If you need a non-linear regression model and you want to insert several independent variables, well, there are other more advanced tools. The last one we'll talk today, it's a binary logistic model. A binary logistic model, it's a model which is able to predict a nominal variable. So until now, you could include nominal variables somehow into the independent variable, among the independent variables, but the dependent one must be scale. The binary logistic, it's a way to predict a binary nominal and only binary nominal variable. Let's see how. The problem of predicting a binary nominal is that you don't have a range of values on the vertical axis. You have only two values, one here and one here. Okay, so you typically have this problem here. These are your charts. Okay, you have one value here, usually 0, and one value here, usually 1. If you use a line, well, the line will predict also values which are far away from 0 and 1. Okay, and since your data instead will be more or less here, some will be 1 and some will be 0. Using a line, you can see the line will pass very far away from the data. Instead, it's much better to use a function which has this shape here. This is called logistic function. As you can see, it passes more close to the points, in particular here and here. Obviously, it passes far away from these points here, but that is something you cannot catch. So, using a line like such as the blue line passes much closer to the points you need. This is called logistic model. So you change the shape of your function to a logistic function. It's here. Analyze regression. Binary logistic. You put the dependent, which must be a binary nominal. For example, well, trying to predict sex, it's not. Let's try to predict whether you have passed decision theory or not. So, have you passed decision theory or not, based on how many exams you have passed. So let's see whether the number of passed exams, it's a good indication to whether you have passed or not decision theory. Okay. Press OK. You get a very long output. You can see from here it has two blocks, block 0 and block 1. Well, if you want to look at the results, jump to block 1. Okay. These are the R square, these two. There are two R square, the Cox and Snell and the Nagelkerke. Both are ridiculously low. It means that the number of passed exams is not able to predict decision theory. Probably there will be people who have few passed exams but have passed decision theory, and people who have many passed exams but have passed decision theory. Okay. It gives you also other estimation which you may examine yourself in case you need this in your future student life. Okay, and here the coefficients. The beta coefficient for exams 0.09. Let's try to do another one. Let's see if I catch one which works. Binary logistic. Unfortunately, working with false data, so data you have, many of you have invented, it's not does not give us many good results. Instead of decision theory, let's well, live with other students, including participation, passed exams, and year of birth. So you can put also several independent variable. You can put also binary nominal independent variables here. Okay. Block 1. R square has improved a little bit, but it's not such a big R square. You can see that participation is the one which gives us the best beta, the beta coefficient. It means that when participation improves, also the probability of living with other students improves. Okay, you have the usual exercises here. Okay. And let's talk about non-parametric tests. Okay. We have already discussed about some basic non-parametric tests. Let's go into detail of other non-parametric tests. Non-parametric tests have a philosophy behind. The philosophy is that the value of the numbers doesn't count. The only thing which counts for non-parametric test is the order of the data. So for example, if your data are 2, 5, 6 and 7, or 2, 5, 6, 999, for a non-parametric test, this data will be considered the same. Okay. So they are well suited whenever the order is important and not the effective value. For example, income. Well, if you have a person who is rich or a person who is very rich, usually doesn't change so much. Okay. Or other situations which you may find in other problems. Another good feature of non-parametric test is the fact that it does not have such a strong assumption as the parametric test, which say statistical tests have always some assumptions, so make some assumption on your data. I don't want to go into the details which assumption, what they are, how to check them. However, non-parametric tests usually don't have so many assumptions, and so are widely used for this reason. Okay, we have already seen chi-square and Spearman correlation. Okay, so let's see the other ones. So the non-parametric test always, as you can see from here, look at the position of the distribution. So the fact that this person is the last one doesn't matter whether it has 6, 7 or 999. While parametric tests look at the numbers, many times they check the average values. Let's see the 3 non-parametric tests that we will discuss. Mann-Whitney. Mann-Whitney is exactly this test here. Let's go to Mann-Whitney. Is the student t-test for true population. With the difference that the student t-test for true population is a parametric test which checks whether the averages are different, while the Mann-Whitney is a non-parametric test and checks whether the position of the distributions are different. So it checks, I have to clear the file, whether these are your x's, your distributions, this is the distribution for population A, and this is the distribution for population B, have a different position or not. In this case, you can see they have a different position. Distribution blue is shifted to the right, okay, and they have also a different shape, but this is not important for Mann-Whitney. Mann-Whitney simply checks whether one is evidently shifted with respect to the other one. It's the same as student t-test, with the difference that student t-test checks only the average. So student t-test will check the expected value, which will be here and probably more or less here. So we'll check whether there is a significant difference between these two expected values. The Mann-Whitney, on the other hand, checks whether the position is really shifted. So it's, from another point of view, more interesting in several situations. Let's see. So let's see how to do it. Independent samples, it's among the non-parametric tests. Analyze non-parametric test, independent samples. Compare and customize analysis. Okay. Here you can see the variable which you want to test. So let's check whether the distribution of passed exams is different between between male and female. Okay. It's the same thing that we have done when we were talking about student t-test for true populations, with the difference that student t-test was analyzing the averages and Mann-Whitney is analyzing the position. Settings, customize test, Mann-Whitney U. Run. It gives you a straightforward answer. Significance 0.64, retained the null hypothesis. It means that the two distributions, so the distribution of passed exams for male and the distribution of passed exams for female, overlap a lot, and so you cannot say that they are clearly shifted. Let's see another one. Mann-Whitney, let's leave. Fields. Year of birth between degree type. So degree type are master or bachelor. I imagine there should be a significant shift here because I assume that master students are born before bachelor students. So I should see a significance difference here, significance difference here, and significance 0.000, reject the null hypothesis. Can you see the null hypothesis that the positions are the same? You reject, so there is a significant shift. Unfortunately, it doesn't tell me in which direction. Okay. In order to get to know it, I will have to plot the two histograms. So if you really want to know in which direction, you should cancel. You should split your file by Where is degree code, degree type, degree type? Compare the groups. And now you should ask for the histogram of past exams. Oh no, of year of birth. And you will see that the histogram for year of birth bachelor is like this one, and for year of birth master is like this one. Oh, let's put the same. Here there is the stupid person who has answered. Master is more shifted to the right. Ah no, 1991, 1996. So let's also put here 1996. Okay. Finally. Oh, now 1976, 1996. Okay, they are more or less the same. You see that master are more shifted to the left. So they arrive up to 1985 and stop, while here people arrive 1986 and 1991 also. Okay, let's go on. Kruskal-Wallis. Kruskal-Wallis is the alternative for the ANOVA test. So it's exactly like the previous one, Mann-Whitney, with the difference that it checks several populations. So instead of checking two populations, it checks several populations. So let's see how to do it. It's identical. Analyze non-parametric test independent samples. Please go to settings and choose Kruskal-Wallis. Remove this one, remove this one. Okay, let's check the past exams by favorite subject. Favorite subject, it's a nominal variable with several categories instead. So you may not use the Mann-Whitney, which is able to check only for two categories. Kruskal-Wallis. So Kruskal-Wallis is the extension of the Mann-Whitney, exactly as ANOVA is the extension of the student test. Settings, Kruskal-Wallis. Ah, sorry, there is a problem. I have the file split. So I've forgotten that my file, as you can see from here, was split. So I should remove the splitting before. So this to show you that it's important in the exam. If I ask you to split the file, and then at a certain point I ask you, don't split anymore, remove the splitting, you do to remove the splitting, otherwise. Okay, now remove the splitting and redo the non-parametric test. Kruskal-Wallis. Retain the null hypothesis. It means that there is no significant difference in the position of past exams, depending on which one is your favorite subject. Okay, let's see whether there is a significant difference of year of birth. Maybe older people prefer some subjects. Reject the null hypothesis. In fact, there is a significant difference in year of birth depending on which one is your favorite subject. As usual, it doesn't tell us in which direction and which is the category which is different from the others. The last test that we are going to analyze today is the Wilcoxon matched pair signed rank test, which is the exact non-parametric alternative to this one, student test for paired data. So you have data which are paired. Okay. I have explained here, for example, grade in mathematics A and grade in mathematics B. Okay. And you want a test which checks whether there is a difference between the grade in mathematics A and the grade in mathematics B. Okay. While the student test checks whether there is a difference in the expected value, so in the average, this one tells you whether there is a difference in the position. Okay. Well, let's use, for example, related samples. It's related sample because the two data are paired, so related samples. Customized analysis, fields, year of birth, and first year of clearly, there must be a shift in the distribution of year of birth and first year of elementary school, because first year of elementary school must be significantly larger for everybody with respect to year of birth. Okay, settings, customized test, Wilcoxon. Please don't leave this one, because if I catch that you're doing all the tests, I will mark it as an error. So decide yourself which test to do. And obviously reject the null hypothesis. There is a significance difference. Okay, let's see another example. For this one, however, we have to open coupled data. These were the coupled data for product A and product B. Let's see whether there is a significance difference between product A and product B. Related samples, customized analysis, product A and product B. Retain the null hypothesis. It means that the distribution of product A is not shifted with respect to the distribution of product B. So the two distributions overlap a lot. Okay, again, other exercises. Whenever at exam I talk about the order of or the position of, it's a clear and evident indication that you should use a non-parametric test. So the order of and the position of are non-parametric tests. Okay? The average, or if I don't specify anything, parametric test. So the order of, the position of, it's an indication that the test should be non-parametric. Okay, we stop here.